Okay. So we're going to continue on with our dosing quiz here. The next question, your patient was diagnosed with an arrhythmia. The doctor wants to give an IV bolus loading dose. So an IV bolus loading dose. Oopsie. No, we don't want that one. Don't want that one. An IV bolus loading dose to start a new constant infusion of Hardenew. The target is 25 micrograms per ml, which is the same thing as milligrams per liter, right? So to determine the loading dose, and it's going to be an IV bolus, so we just need our target concentration. As far as we know, there's no drug on board, so we're going to have our target concentration of 25 milligrams per liter. Although maybe I should change it now that I see this as milliliters. This is liters. Okay, we're in liters for our volume. So our volume is 0.5 liters per kilogram. And they weigh 70 kilograms. So we don't have to adjust for bioavailability because we're giving it IV. Get my calculator, sorry. So 70 times 0.5, I know that's 35 times 25. So 35 times 20, oopsie. 35 times 25 is 875. And our units are liters, kilograms, are milligrams. So it's 875 milligram loading dose, but we want to round to the nearest 100 increment. So we're going to give 900 milligram loading dose. And then our constant infusion, again, we're still shooting for a CSS of 25. Again, micrograms per milliliter. Okay, and I'm going to leave it in milliliters because our clearance is in milliliters. So our clearance is 25 milliliters per kilogram per hour. And our patient weighs 70 kilograms. I need to move this a little bit. Okay, times 70 kilograms to solve for our dose rate. And because we're giving it IV, the bioavailability is 1. Our kilograms will cancel. We have milliliters per hour. So the milliliters will cancel. And our answer is going to be in micrograms per hour. But our rate is going to be in milligrams per hour. So we're going to have to change this to milligrams per hour once we figure it out. So it's 70 times 25 times 25. So I got 43,750 micrograms per hour. So we're going to move this by 3 decimal points. And so we've got 43.75 milligrams per hour. And we're going to round to the nearest 5 milligram increment. So we're going to round this to 45, aren't we? 45 milligrams per hour. Okay, good. Now, what's our next? What CSS? Oopsie. What CSS do we expect at this regimen? So we had to round up a little bit, right? So we're going to be a little bit higher than our goal of 25 milligrams per liter. So what is our CSS will we expect when we give this dose? Okay, so our CSS is going to be equal to our dose rate, which is 40 5 milligrams per hour. And our clearance is 25 milliliters per kilogram per hour, times 70 kilograms. So our kilograms cancel and our hours cancel. Wait, yeah, and our hours cancel, but we'll have milligrams per milliliter. So we want to be in milligrams per liter. So there's 1,000 milliliters per liter. So I'm going to multiply it times 1 over 1,000. Then our milliliters will cancel here in the denominator. Okay, and then we'll have milligrams per liter, which is what we want. So 20. So I'm going to do the denominator first. 25 times 70 equals divided by 1,000. And divide that into 45. And so I got a CSS of 25.71 milligrams per liter. So if we round to the nearest whole milligram per liter, it'll be 26, just one different than our goal, right? So we shot for 25 and we got 26. All right, next. Our patient has started on drug Y with a target of CSS average of 50 milligrams per liter. We're given the clearance, volume, and bioavailability. I noticed I didn't tell you whether to give it PO or IV. I meant it to be PO. I think most of you figured that out, but I apologize about that. I'm gonna have to fix that question. So how much of drug Y will we give every 8 hours and round to the nearest 10? So this is our maintenance dose. So our CSS average, and the average kind of tips us off. We want to have a CSS of 50 milligrams per liter. And so our bioavailability is 0.85. We're solving for our dose rate. Our clearance is 8 milliliters per kilogram per hour. And our patient weighs 90 kilograms. So times 90 kilograms. The kilograms will cancel. And we have milliliters and liters again. So I'm going to multiply this times 1 over 1,000. So 1,000 milliliters in 1 liter. So those milliliters will cancel. And we have liters that will cancel. And we have milligrams per hour, which is what we want. All right, so we'll figure that out for milligrams per hour. So our dose rate is going to be in milligrams per hour once we do all this calculating. So 8 times 90 divided by 1,000. And then we're going to divide that into, or times 50. And then divide that by 0.85. Right, so I got 42.35 milligrams per hour. And we're going to give this every 8 hours. So we're going to have to multiply this times 8 hours so that we have our dose. So 42.35 times 8. And I got 338.8 milligrams. So we're going to round to the nearest 10. So we're going to recommend 340 milligrams to be given PO. If it were IV, we would just not, that would have to be 1, wouldn't it? So for this dosing regimen in this patient, what would you expect a CSS average of? Okay, so we just need to use this same equation, but this time we're solving for CSS. This whole clearance can remain the same. And our dose rate is going to be 0.85 times our dose rate. And our dose rate was 340 Q8. So if we divide 340 divided by 8, we're going to be giving we're going to be giving 42.5 milligrams per hour. So let's see, this works out to be per hour. So we'll have milligrams per liter, which is what we want, right? So this is going to be in milligrams per liter. So we just need to do our plugging and chugging. So 8, I'm going to do the denominator first. 8 times 90 divided by, wait, that's not right. 8 times 90 divided by 1,000. And then divide that into 0.85 times 42.5. Let's see, did I do that right? Okay, I don't think I did that right. Let's see. Eight. Wait, 340. Sorry. All right, now I did it right. Okay, that works out to be 50.17 milligrams per liter. So round to the nearest whole number, so it's going to be 50. Sorry, I did a little calculating wrong to begin with. Okay. Good. Moving on. Okay, we have another transplant patient taking 150 every 12 hours. Her CSS average is 600 nanograms per ml, which is the same thing as micrograms per liter. The team would like to have a target CSS average of 90 nanograms per ml, 900, I'm sorry. Assume no change in clearance or bioavailability. All right, so her dose is too low. So she's taking 150 every 12 hours. So that's 300 milligrams. So again, if we assume no change in clearance or bioavailability, we can use our proportion, can't we? 300 milligrams per day gives us a concentration of 600 nanograms per mil. And we're going to set that equal to our target of 900 nanograms per mil and see what we come up with. So 300 times 900 divided by 600 gives us 450 milligrams of drug X every 12 hours. So if it's 450 milligrams per day, we're going to divide that in half, aren't we? And so it would be 225 milligrams Q12. And we're going to round to our nearest 10. So this is going to be 230, isn't it? 230. All right. Your patient needs to receive 250 milligrams of Vendrix to be given over 1/2 hour. So it's given over 0.5 hours. Vendrix solution is available as 10 milligrams per ml. So there's 10 milligrams. We're setting this up as a 10 milligrams per 1 ml. So what rate will you tell them to run the solution over 1/2 hour to deliver this dose? So what's the rate? So it should be in mils per hour, right? So our milligrams will cancel and we'll have mils per hour. So this is exactly what we want, isn't it? So 250 divided by 0.5 divided by 10 is 50. So we're going to be running it at a rate of 50 milliliters per hour for 1/2 hour. So that's 50 milliliters per hour for 1/2 hour. Good. And finally, last question. If a drug has a strong dose response relationship, so really that's the holy grail, right? Our dose regimen to a response. That's really what we're looking for, isn't it? But so if we could give the same dosing regimen to everybody and get the same response, we don't need to, we're done. That's all we need to do. But that doesn't always happen. So we ended up having this intermediary of a concentration. And so if you know the dose to response relationship, if it's a strong dose response relationship, there's no need for therapeutic drug monitoring, right? Because we know we can give the same dosing regimen to everybody and they get the same response. So if that's happened, then we TDM is out. And also if there's a weak concentration response, remember concentration response, we have to be able to count on the concentration response because usually what we're doing is measuring the concentration with TDM and we are assured that a certain concentration will give a certain response. If that isn't there, there's no point in doing TDM either. So this is false. Both of these things make it so that you don't use TDM. When you do use TDM is if you don't have, so if the drug does not have a strong dose relationship and a strong concentration response relationship occurs, then therapeutic, that would make it true. All right, great. Thanks for your attention. Go get them. Bye.